Okay, many students are not here, but still we have to start almost on time. Today I had two plans. One plan is to go through all the test questions and revise the concepts so that you can be thorough on what you learnt. Second option is to teach you some other thing like perpendicular magnetic recording or something like that. Okay, so what do you prefer? Going through all these questions, revise what we learnt, or perpendicular magnetic recording? Okay, if you are shy, maybe I ask you a question through OOClap. Okay, just so raise hands. Okay. So one is revision of the topic that we learnt by going through the questions. Okay, how many of you want to have revision? 1, 2, 3, 4. Okay, how many of you want to learn some new topic like perpendicular magnetic recording? 1, 2, 3, 4, 5, 6. Okay, they are the winners. So let's go through some more concepts. So let me start from here. So when I started discussing the growth of magnetic recording, I told you that scaling was one way in which growth is achieved. So we have been scaling down the grain diameter, we have been scaling down the thickness, okay, and making the bits smaller in length, narrower in width, and so on. Okay, so this leads to the problem that the grains are now smaller in volume. So when the grain becomes smaller and smaller in volume, the KUV becomes lower and lower. Okay, KUV, the energy that retains the magnetization in a particular direction becomes lower and lower. So you will notice that when the volume is bigger, the magnetization is stable as a function of time, but as the volume gets smaller and smaller, the fluctuation frequency becomes more and more. Okay. So you can see 8 nanometer flips more rapidly than 8.5 nanometer cube of cobalt. Okay. So this problem is called thermal stability, and so even if you do not apply any magnetic field, the remnant magnetization might decay as a function of time. So in this measurement, even when there is no magnetic field, you can see that the magnetization decays as a function of time because of the competition between two energies, which are the anisotropy energy and thermal energy. Okay. Then this was explained by Neil Arrhenius decay. So where they said the decay of magnetization is based on a time constant, which is an exponential function of the ratio of KUV and KBT. Okay. So if KUV by KBT is large, tau will be large. If tau is large, decay will be less. But if KUV by KBT is small, tau is small. When tau is small, denominator is small. So this will be a large number, negative number. So the decay will be significant. Okay. So this results in the observation of a super paramagnetism. Okay. So when you make particles larger, the particles will retain the magnetization in certain time in a certain direction for long periods of time. So suppose I had magnetized all these grains pointing up, you observe after 10 years also they will be in this direction for 10 years, for example. So if KUV by KBT is more than 60. So, this retention will be for about 10 years. Okay. On the other hand, if I make the particle small, let us say I initially magnetize along this direction, but after I remove the magnetic field, so some of them would be in other direction. So, you observe these particles, they will be keep fluctuating as a function of time, like the animation that I showed you. So, because of that reason, these materials do not have a hysteresis. Okay. Superparamagnetic materials do not have a coercivity, but they do have a large magnetization, because these are still ferromagnetic particles. Within these particles, the spins are still parallel to each other. Okay. Do you think superparamagnetic particles have no use? Does anyone think that superparamagnetic particles have no use? Can you suggest some use for superparamagnetic particles?
They are used in biomedical applications.
Which application exactly?
Drug delivery.
Pardon?
Drug delivery or something.
Drug delivery.
Nanoparticles, superparamagnetic nanoparticles.
Okay. You are almost 90% right. Okay. These superparamagnetic particles are used, potentially useful in some application called magnetic hyperthermia. Okay, hyperthermia means let us say your body cell temperature is increased beyond certain temperature, right. For example, if the temperature is more than 42 degrees Celsius or 44 degrees Celsius, the cells will, if it let us say 50 degrees Celsius to be safe, let us say if the temperature of your body cells are at some high temperature, the cells will die. Okay. So, at slightly high temperature, cells will die, that is called the hyperthermia. So, this magnetic hyperthermia is a treatment people are looking at. Okay, let me break this here. So, magnetic hyperthermia is a treatment people are considering to get cure cancer. Okay. So, if you compare the temperature at which the cells die, okay, let us say the normal cells die at around 50 degrees Celsius, the cancer cells die at a slightly lower temperature of around 42 degrees Celsius, for example. Okay. So, there is a difference at which different cells die. So, normal cells can tolerate slightly much higher temperature compared to, these numbers you do not take for granted, I am giving some rough numbers. Okay. Cancer cells die slightly at lower temperature. Okay. So, if this is the case, let us say at some place there is cancer. So, let us say you inject some particles here. Okay. So, these are magnetic nanoparticles. Okay. So, you inject magnetic nanoparticles and magnetize them up and down. Okay. So, you let the particles undergo through lots of hysteresis loop. Okay. So, you magnetize them, demagnetize them, magnetize them, demagnetize them, do this for like this hysteresis loop is carried out in several hundreds of kilohertz. Okay. So, you are doing this operation at very high frequency. Okay. That means, even within 1 second there are so many hysteresis loop traced. Okay. You know that the area under this curve is the energy spent. Okay. So, if you have a hysteresis loop, you go through one loop, that means basically you have spent some energy. Okay. So, when you inject nanoparticle and you let them undergo so many hysteresis loop, basically energy spent. So, this energy will result in rise in temperature. Okay. So, by controlling the time and the number of nanoparticles that you have, you can reach at this temperature, for example. Okay. So, if your body temperature is 38 or whatsoever 36 degree. So, from 36 degree Celsius you go to 42 degree Celsius by carrying out a hysteresis loop of these magnetic nanoparticles. Okay. So, this is how you raise the temperature of the cancer cells to 42 degree Celsius and you can kill the cancer cells. Okay. So, this treatment is called magnetic hyperthermia. Okay. So, here I am saying that the super paramagnetic particles are useful. Okay. So, do you find any contradiction in whatever I am saying? First of all, I said super paramagnetic materials have no hysteresis loop. Okay. They have saturation magnetization, but they have no hysteresis loop. And here I said if you have hysteresis loop, then there is some energy, that energy is the one that gives rise to this temperature increase. So, I am contradicting, right? So, what is the difference? How the super paramagnetic materials are useful? Yeah, nano, so you can send them easily through the veins and things like that. So, that's one thing, but there will be no big difference between say 8 nanometer super paramagnetic particle versus say 20 nanometer non super paramagnetic particle. There will be no difference in sending them to your body, that is not the difference. Okay. So, first of all, why super paramagnetic particles are useful? If you ask why super paramagnetic particles are useful, so to answer this question, let us assume that the particles are not super paramagnetic. Okay, if the particles are not super paramagnetic, so they will have certain, these are all single domain particles, so they will have certain magnetization direction. Okay. Okay, so when they are not super paramagnetic, they will have a fixed magnetization direction. So, when you put them together, they will agglomerate in such a way that I mean the north south poles, they will get sticking, they will start getting sticking and so on. Okay. So, when they are not superparamagnetic, the particles will get agglomerated. Okay, so they have a remnant magnetization. That means when they are not superparamagnetic, they will have a remnant magnetization. Remnant magnetization is not 0. That means they have north pole, south pole. So, they will all get closer to each other, like two magnets stick to each other. So, all these particles will get agglomerated. Okay. So, if that is the case, we cannot use, suppose you make many number of particles, right, they will all agglomerate together, then it is difficult to inject these particles into the cancer cells. Okay. So, what you want is, you want to have a fluid. So, in this fluid you want these superparamagnetic nanoparticles to be isolated from each other. So, you do not want them to get attracted. Okay. So, for this reason we want superparamagnetic particles, because superparamagnetic particles have 0 magnetization. That means they have no fixed north pole, south pole. So, they will not get agglomerated. Okay. So, for this reason superparamagnetic particles are desired for magnetic hyperthermia. And now, let us come to the second point. So, I told you that superparamagnetic materials have no hysteresis loop, coercivity is 0, but I said the energy product of, the energy spent is coming from hysteresis loop. So, there should be some coercivity, right. So, these two are contradicting with each other. So, why or how I am right in saying that we can use superparamagnetic particles? Okay. So, when you have a superparamagnetic particle, we are talking about a time dependent everything, time dependent magnetization, which depends on this, right. So, if you remember, I told you we are doing this at hundreds of kilohertz. So, when we measure hysteresis loop of superparamagnetic particle, what is the time scale we are talking about? Okay. So, time scale is like, maybe we hold the data for, we hold a magnetic field for say maybe 5 seconds or 10 seconds, something like that. So, we are talking about few seconds of time scale in which the hysteresis loop is measured. So, we will not see any coercivity for superparamagnetic particle. So, if you keep a collection of superparamagnetic particles in some fluid, you observe the fluid, you are going to talk about some long time scales longer than seconds. So, whether we keep the superparamagnetic particles stored or we measure the hysteresis loop of superparamagnetic particles using a VSM, we are talking about few seconds, but when we do hyperthermia, we are magnetizing and demagnetizing the superparamagnetic particles at hundreds of kilohertz. Okay. So, kilohertz is milliseconds. So, hundreds of kilohertz will be, we are talking about 10 microsecond kind of time scale. Okay. So, there are some equations people have derived based on this formula. We can actually derive an equation for coercivity as a function of time. Okay. So, if there is small KUV by KBT, coercivity also will be a function of time. So, it will be some H naught plus something which is actually a function of time. Okay. I do not remember the exact numbers here, but there will be something here which says that the coercivity will be function of time, and that will give you a time dependent coercivity which will look something like this. Okay. So, at longer time scales the coercivity is small, low coercivity, but if you go towards smaller time scales, the coercivity will go higher and higher. Okay. So, this depends on KUV by KBT. Okay. Let us say KUV by KBT is, let us say this is 0, let us say this is something like 10 kilovolt. Okay. So, the time dependent coercivity will look like this. So, in this graph, out of these 4 graphs, which one represents large KUV by KBT? Which color represents the largest KUV by KBT? Green. Okay. So, this, I mean, when KUV by KBT is very large, suppose it is even much larger, it will be something like this. Okay. Coercivity will be almost independent of time if KUV by KBT is very large. Okay. So, for intermediate KUV by KBT, you will be here. So, if KUV by KBT is very small, you are here. If it is too small, then you will reach even this point, that the coercivity becomes 0. Okay. So, let us say this is seconds, this is kiloseconds, sorry milliseconds, let us say this is microseconds, nanoseconds and so on. Okay. So, we are choosing some particles either here or here. Okay, but if you are doing operation at microseconds range, these particles will have some coercivity. Okay. So, when you do the hyperthermia, the superparamagnetic materials will have hysteresis loop like this. So, either at a small time scale you will see this, or at low temperature you will see this. So, superparamagnetic materials may show a hysteresis loop at low temperature or at small temperature, small time scale. Okay, let me erase this one, this is going to confuse you. Okay, so, at small scales super paramagnetic materials will still have a hysteresis loop and they have a coercivity. So, you are using this energy to raise the temperature of cancer cells and kill cancer. So, when you store them, we are talking about some time scale like this where they have no coercivity. So, when you have stored them in the solution, their magnetization is fluctuating as a function of time without any magnetic field. But when you go here, you apply magnetic field, they respond to the direction of your applied field. Okay. So, this is one application of super paramagnetism. Any other questions here? But in hard disk technology, super paramagnetism is a problem in two aspects. First aspect is that you will lose your data, okay, because you are storing. So, let us say you have a coercivity as a function of time looks like this. Let us say this is say a few seconds. Here we are talking about years. Here we are talking about say a few nanoseconds. Time and coercivity. So, when you do VSM, you will observe this kind of coercivity. Okay. But if you extrapolate for 10 years, they have very low coercivity. Because of this reason, they cannot retain the information for a long period of time. Okay, that is one problem. Okay, retention is the problem. Another problem you see is here. Okay. So, when we write data in hard disk drive, we are writing data so fast that like you write one bit like this, another bit like this, another one like this. So, you keep writing data. So, this writing time scale is around 10 nanosecond. Okay. So, if you have a time dependent coercivity which looks like this, what happens is when you are writing information, the recording media has a very large coercivity. Okay. So, that means your writability is going to be difficult. So, these are two implications of super paramagnetism. So, it is a problem in hard disk drives, but it is useful in concepts like magnetic hyperthermia. Okay. So, in hard disk, if you are making the grains smaller and smaller, you will have the problem of data loss. Okay. So, this we have seen before. If you make the grains smaller and smaller in volume, then your data is not stored for many years. Ideally, once you magnetize, they should be like retaining the pink and blue, but if the grains are too small, some pink will become blue, blue will become pink. Okay, blue and pink represent north and south poles, for example. Okay, if you make them smaller and smaller, the data is not retained. So, you cannot read 1 or 0. Here you can say this is 1, this is 0, but here and they have reached this kind of small volume, they do not retain the 1s and 0s perfectly. Here you cannot make out 1 or 0. Okay. So, this is the problem. Let us skip questions. So, when we keep scaling, we encounter the thermal stability problem. Then I also told that the technology progresses by making many technological jumps. Okay. So, we look for jump from one technology to a totally different technology. Okay. For example, when the hard disk drive was made in 1956, the magnetic recording media were made from magnetic particles dispersed onto some substrate. Okay, so, how they made the hard disk media is based on this paint. Okay, so, this is basically a paint. So, it has some solvent and magnetic particles are dissolved in that solution. Okay, basically it is a solution embedded with iron oxide particles. Okay. You know how they made the particles uniform? They filter using a SOX kind of thing. They filter all the particles, then they pour this paint onto a spinning disc. That is how they coated the magnetic recording media, the first magnetic recording media. So, this was the kind of technology for many years until 1980s, then where they switched to the thin film media. So, okay. The sputtering comes into picture only in 1980s. Okay. So, making the jump from particle based media to sputtered thin film media is one kind of technological jump. Okay. It is not easy. Okay. It involves a lot of risk for company. So, hard disk media moved from this spin coating to sputtering. Also, as I mentioned, the head was basically a coil manually wound, and they used the same coil for reading and so on. But nowadays we are using machines like this to sputter the hard disk drives. So, the hard disk drive equipment, the disk media manufacturing equipment has around 20 plus chambers. Okay. So, these are like modular machines. So, for example, let us say you have module 1, 2. So, you can have until n, then you will have n plus 1, n plus 2 all the way to 2n here. Okay, so, if you want 20 chambers, this n will be 10. If you want to 22, there will be another 2 and so on. So, you can keep adding more modules. So, you can keep increasing the number of chambers if you want. Okay. Suppose the layers required for magnetic recording getting more and more, you just add more module. Okay. So, if you make n is equal to 13, you will have 26 chambers. Okay. So, people can increase the chambers if they want, and so here we are loading all the disk in class 10 clean room. So, I told you what is a class 10, right. That means you have, let us say 1 cubic meter, within that 1 cubic meter you will find only 10 particles. Okay. So, in this room, for example, you may be able to spot 10,000 to 100,000, okay, this room, but in the class 10 clean room this number of particles is just 10. So, that is the kind of clean room where they load the disk and so on, and this whole operation is completely automated, no human touches anything. Okay. So, the loading, unloading, everything is automated, no humans involved. So, the disks are clean. So, why we do such clean operation? Why not have a few particles here and there? Okay, so, in hard disk, as I mentioned, we have a disk that is rotating, then we have a head that flies over the hard disk, okay, and reads or write information. Okay, so this you learned. Do you know what is the spacing between the disk and the head that flies over the disk? What is the spacing? This spacing used to be micrometers in the past, okay, but currently this spacing is 1 nanometer. So, the spacing between the head and the disk is 1 nanometer. So, if the spacing is 1 nanometer, if you have one particle which is even say few hundred nanometer, and particles are typically micrometer, right. So, they will cause crash. It is like you are trying to land a plane, but there is a rock in your runway. Okay. So, there will be crash, then the hard disk will be spoiled. So, they want to minimize all this contamination. Okay. That is why we operate in the class 10 clean room, and we make the disk everything clean. So, if you are going into the area where this sputtering is going to happen, right. So, in companies you have to like fully cover up. So, your head, everything is covered up except your eyes and your gloves, and in some companies even after you wear the gloves, you are supposed to wash your gloves in the tap, only then you can go. And this gloves will be like you are wearing a suit, and this gloves will be like hold tight by something. Okay. So, you are fully covered. So, if you go in, you are not going to contaminate the clean room. Okay. That is something. Then usually most clean rooms, right, they do not allow people with say makeup. Okay. So, if you are working in the clean room, you are not supposed to wear makeup, because you will be generating some organic contaminant. They can spoil the performance of the things that we do. Okay. So, technologies like hard disk, MRAM, these are all very highly sophisticated technology. And here I also want to say something about discipline. Few years ago, right, I mean these days people can buy a lot of electronic things in India, but a few years ago people tried to get say TV or whatsoever from foreign countries, and when they bring something, let us say we bring a Sony product to India. Okay, Sony has many factories. For example, there may be a Sony factory in Japan, they may have Sony factory in Philippines or China, something like that. Okay, many companies, I mean many countries where the same company may make product, but people will still prefer the products made in Japan. So, I used to wonder why it is the same company. So, there should be same quality in the products that Sony makes. So, why distinguish between something made in Japan or Philippines? I used to wonder, but later at some point of time I realized that there is some difference between the countries in which some product get manufactured. That is from this aspect. Okay. So, to give you some anecdote, I went to some factory in some European country. Okay, I won't name the country, but some country in Europe. So, you will still associate some discipline with Europe, right. But in that company they were making hard disk drives like this. So, you are supposed to maintain everything, you are supposed to be gloved, and everything has to be completely protected. When we went to that factory, the guy who is working in that company, he got a phone call and he picked up the phone from his pocket and started talking. Okay. This is completely not allowed when you are talking about operation like this. Your phone, you cannot take it out. Everything is supposed to be clean, and your phone is outside, its phone is contaminated material. And if you use the phone in the clean room, then let us say you are making some batch of hard disks. So, those batch is going to be spoiled. Okay. So, because he flipped the phone out, so there will be some thousands of disk which would have contaminated. Okay. So, the disk drives, those which use this disk drive, they would be like spoiled, I think. They may get spoiled over a period of time. Okay. So, this brings us to this concept of discipline. So, if this happens in Japan, I mean it will never happen in Japan. Okay. Japan is so disciplined, the Japanese people are so disciplined, they won't do this. Okay. Even they may not even carry the phone inside the clean room, but if you lack discipline, this might happen. Okay. So, the product you make will be different, even if it is Sony, right, depending on the discipline of people, we may have poor product or good product. Okay. So, this is very important. So, you are all going to be researchers, and some of you may work in the industry. So, please follow the protocols. Okay, whether you are doing research or even driving or riding bike, follow the rules. Okay. Now, let us come back to science again. Okay, so there have been lot of technological jumps like this. So, particulate media to thin film media. Then if you take head, we learnt about inductive heads, magnetoresistive heads, GMR, TMR and so on. Okay. So, these are the technological jumps through which we move towards high density. Okay. So, in that sense, let us come to the second topic, which is called the perpendicular recording media topic. So far I have been mostly talking about the longitudinal magnetic recording technology, where the magnetization of the disk media is parallel to the disk surface. Okay. On the other hand, perpendicular recording media has two differences. One difference is that the magnetization is lying out of plane. So, your north south poles are up or down. Okay. So, this is one difference between longitudinal recording media and another the perpendicular recording technology. Secondly, you will also see that there is a second magnetic layer. Okay. So, we have one ferromagnetic layer which stores the information. So, you also notice that there is a soft magnetic underlayer in perpendicular recording. Okay. So, this perpendicular recording technology uses this soft magnetic underlayer for writing information. Okay. So, before we go here, let me ask a question, then discuss further. Okay, I will use let us say you have a disk with a ferromagnetic particle, you want to magnetize the material to be like this. So, for this I told you that we can use a head like this, then this head will produce some field and this field also will come out and it can write magnetization to be right or left, right. You have a disk like this. Now, here you want to write the bits to be magnetized up or down. What kind of head will you use? So, here you see the magnetic field is going this way. So, it is horizontal. So, you can write horizontal bit. Now, you want to write vertical bits, how will you write? Perpendicular? How can you come and draw? Come. Last day we will have some interaction. Come here.
I mean the magnets align in that direction, north and south, so
Okay.
they will be directing.
I mean, how will you? I mean, I cannot understand what you are talking about. You have to come here, draw, and explain what is in your mind.
For the longitudinal, the direction is along this, so
Mhm.
this is north and south.
Yeah.
But to make it perpendicular, we need to have alignment like this.
Yeah, I mean, how will your head produce electromagnetic field? You have to use some electromagnetic field, right? I mean, electromagnet to generate magnetic field, that has to make the magnetization up or down. So, how will the head look like?
The external magnetic field should be in this or this direction.
Yeah, so
Only
how will you design a head to achieve that? Okay, anyone else? Okay, thank you. Anyone else has, yeah. Huh? Circular toroid type. Okay, so you are saying that you want to have some toroid which will produce magnetic field in the vertical direction. Okay. I mean, in some sense, this is also toroid, right? Your coil is a. So you mean like this?
This insertion controls the like field structure, no?
Okay, maybe you come here and draw.
Like we having a toroid on this, so towards the center we have the field either in this direction or in the opposite direction. So could that work?
Okay, so that will produce a magnetic field, but where is the return path? Return path for the magnetic field.
In this.
We need some return path, right?
Yeah, in this, like towards the center, it will be the fields are in this direction, right? In this, if you change the current, the
So it's going to be like this, is it?
yeah.
Okay, thank you. So, in the very early version of perpendicular magnetic recording, what they did is something similar to what you suggested. So, you have a coil, then they have a ferromagnetic core, okay. Then the disc media, I mean this is some kind of return pole or whatsoever you can say, and they keep the disc media like this, okay. But the next question is, let us say you have a disc. So, I told you that the disc has two surfaces and both sides have magnetic film, and we are writing information on both sides. So, we store say 500 gigabyte of data here, 500 gigabyte of data on the other side. So, if you have a head like this, how will you write on both sides? So, when you try to write here, then it will erase the data here. Okay. How will you do that? Okay, so this was the first concept, I think 1980s, somewhere there. So, they realized that you cannot write on both sides of the disk. Then they came up with this concept called single pole head. So, now the head will look something like this. Okay, I told you that disk media has a soft magnetic underlayer. Okay, so this is the layer that stores the information. So, storing happens here, but below this layer there is a soft magnetic underlayer. There will be some layer to separate these two. Let us ignore them for the time being. Let us just imagine that there are two ferromagnetic layers. Okay. So, this layer is a harder layer with a coercivity of say 6 kilovolts to store information. This is the soft magnetic underlayer with a coercivity, very low coercivity layer, say a few volts. Okay. So, when we talk about electromagnetic writers, again we are talking about some soft magnetic material as a core of the electromagnet. So, that is why I have used the same color code blue representing both the ferromagnetic core as well as the soft magnetic underlayer in perpendicular recording technology. They are soft material with a low coercivity, low resonance and so on. Okay, so, when you write information, you send a current through this head. Okay, it produces flux line shown by the yellow lines. Okay, so, this yellow lines will go through the soft magnetic underlayer like this. Okay, so, when you energize the coil of the electromagnet, it will produce a set of flux lines. So, magnetic flux lines always follow a closed path, right. So, they go through the recording layer, then this soft magnetic material passes them back to the other side of the head. Okay. So, this is how the writing happens. Okay. To give you some perspective of how beautiful this design is, let me also explain another concept. So, when we design longitudinal recording media, right, longitudinal recording technology, we have electromagnet, we send current. So, this current produces magnetic flux lines, the flux lines go through the gap, they also go through outside. So, we call this as fringing field. Okay, so, we are using the fringing field to write information. So, if you look at the values of the gap field and the fringing field, gap field is usually 2 times larger than the fringing field. Okay. Your field is more here, the gap, and your field here is less. So, we are using the weaker field to write information in longitudinal recording. Let us say you have certain material here, this can produce a gap field of say 15,000 Oersted, fringing field will be like 7,000, 8,000 kind of Oersted. Okay. So, we are using this 7,000 Oersted to write information in longitudinal recording. So, we are not using, we cannot exploit the gap field for writing information in longitudinal recording technology. So, this is a problem. Now, let us come to the other design. So, in perpendicular recording technology, we have this kind of design. So, magnetic flux line go through this fashion. Okay. So, can you see something here interesting? What is interesting in this design?
Strength of the field.
Pardon?
Strength of the field while writing.
What field?
That is strength of the field.
Is higher. Why?
Because we have concentrated it in narrow region.
Yeah. So, if I rotate this by 90 degree, okay, so I rotate this by 90 degree. Now, you look at this one. So, these flux lines look very similar to the longitudinal recording technology flux line, and if you notice the disc media, which is the black color, it is in the gap field. Okay. So, in perpendicular recording technology, by this, I mean, if I am rotating this way, right, but virtually we are using the gap field to write information. Okay. So, instead of the 7000 Oersted, what we have been using in longitudinal recording technology, now we have, with this design, we are using much larger field to write information. Okay, so, this is the design they came up with. So, by using a soft magnetic underlayer and by using a head like this, they can produce high magnetic field here. So, this magnetic field goes up or down. Okay. So, it will be either coming down, creating down magnetization, or it may be going up, creating up magnetization. Okay. So, this is how we magnetize the material to point up or down. Okay, so, this head is called a single pole head. So, before I describe this name, anyone sees any problem here? Magnetic flux line go through this region, magnetic flux line go through this region, any problem? If it magnetizes this region down, will it magnetize this region up? Because the magnetic field is coming this way, then going back this way. Right?
Going in another direction, but it is very weak. I mean, flux through particular area is weak. So it
Okay.
will be enough to.
Yes. Okay. So, you know that the magnetic field strength is phi over A, right? The area here is smaller. So, you are concentrating more flux here. So, the strength at this point will be larger. You are producing large magnetic field here, but when it comes to this region, this part of the head is a wider, a large area. So, the flux is not that concentrated, your area is large. So, the magnetic field you produce here is not large enough. Okay. Okay. So, basically you are using only one pole for writing information. So, because of that reason it is called single pole head. Okay. So, even though you have two poles, effectively only this pole is writing information. So, it is called a single pole head, and this pole is called the return pole. The flux lines return via this pole. So, it is called return pole, and this is the writing pole. So, if you compare the field strength at this pole and the other pole, right. So, the writing pole may produce 15,000 Oersted, okay, whereas this return pole may produce a field of around 1500 Oersted. Okay. It still produces some magnetic field of the order of 1500 worsted. So, because of this reason, when people design perpendicular recording media, they design the recording media in such a way that this field called nucleation field is more than what you see here. Suppose 1500 kind of field is seen here, you have to design recording media with a nucleation field of more than 2000 worsted. So, I defined this earlier. Nucleation field is the field at which like only 5% of magnetization switches, I mean 5% drop in MS. Okay. That means very few grains switch at nucleation field. Okay. So, what it means is that you are designing a media where this field does not reverse any grain. Okay. That is basically the concept. Okay, that is about perpendicular recording writing technique. Yeah, so, as I said, the disc will be placed somewhere here, the original configuration. Okay, to write on both sides, let us say you have 1 millimeter thick, you have one head here, another head here, but if I zoom in, both heads produce magnetic field that goes through this way and come back. Okay, so, similarly, this head will produce certain magnetic field, it will write bit, come back through the subtended layer to the other pole. Okay. So, this is how using a single pole head kind of head you can write on both sides of the hard disk. Okay, maybe I will just spend 5 minutes before break. Then after break we will go through the test question. Okay. So, I will satisfy both of you. So, I told you that we are using a sputtering machine with many chambers. That is because if you look at a perpendicular recording media of the current hard disk drive, you will find about 20 layers going from bottom to top. You will find 20 or more. Okay. I am not following the progress now, but I expect it should be more than 20 layers. Okay, so, these are the soft magnetic materials I described. So, the head produces certain magnetic field, it goes through the soft underlayer, then goes back to the other side of the head. Okay. So, you notice that this soft underlayer is not a single layer, it is again a SAF. Okay, so, you have some thin layer of ruthenium and you have at least 2 ferromagnetic layers which are antiferromagnetic coupled. So, here again we are using synthetic antiferromagnetic structure to minimize some noise which we do not go into detail. Then we have some seed layers which help these 2 ruthenium layers to grow with certain epitaxial texture. Over this we have many layers of magnetic material. Okay. So, when I said recording layer in the previous discussion, we assumed that one magnetic layer stores the bits, but in reality the recording layer comprises of many layers. So, you see the I put many layer. Okay, so maybe I will just focus on this one today, why we need many layers of recording material rather than just one recording layer. Okay. I will skip all the other part because we do not have time to discuss everything. So, we learnt about coherent rotation or Stoner-Wohlforth reversal mechanism, where I mentioned that if a particle has an anisotropy constant Ku and if the magnetization is m, wrong mouse. So, if a particle has an anisotropy constant Ku and the magnetization ms, then the anisotropy field required to switch the magnetization is the Hk. Okay. So, if a particle has say 10 power 6 earth per cc, ms of 1000 or 500 mu per cc, you can calculate Hk. So, typical Hk of a hard disk media can be around 20 kilostat. Okay. Whereas, the magnetic field that you can produce by winding a coil and inserting a ferromagnetic core, you may be able to produce almost similar value. Okay. So, this is not much more than the anisotropy constant of the material. So, there may be some difficulty, I mean there may not there may be, there is difficulty to write information on materials with a large anisotropy constant. Okay. So, writing has always been a problem. So, people are trying to come up with various methods to write information. Okay. So, in that sense, if you follow this switching coherent switching mechanism, then you have this problem. Okay. What if you go to some other form of switching, which we call incoherent switching? Okay. So, this is the question people asked, then they came up with methods to achieve incoherent switching. Okay. So, when I described to you the coherent switching, I mentioned that let us say initially your magnetizations are like this. When you apply a reversal magnetic field, so at some point of time these spins will be at this angle, at another point of time they will be like this and so on, right. So, in coherent rotation reversal mechanism, all spins cooperate with each other, they switch together. So, all the spins, let us say you have a grain, cylindrical grain, all the spins in this grain are switching together. Okay. So, there is a harmony between them, like the synchronized swimmers of Olympic swimming, they all collaborate together. Okay. So, when we talk about incoherent switching, what we are discussing is like, let us say initially you are here, initially all the magnetizations are like this. Now, I apply some magnetic field. So, what happens is that this magnetic field changes the magnetization of the top spins, then the next layer spins are not that responsive to the magnetic field. Then the spins at the bottom are like this. Okay. So, you see that there is no coherency like what you see here. The spins at the top behave differently compared to the spins at the bottom. Okay. At another point of time, maybe the spins at the top are like this, then this is like this, then this is like this. Okay. Then at another time, maybe these spins are the top are like this, then like this. Okay. So, you can see that the spins are not switching in a coherent manner, and this switching is called incoherent switching. Okay. So, the beauty of this switching method is that you can switch with a writing field much lower than the anisotropy field of the material. Okay. So, we can achieve this by having materials with two different magnetic property. For example, we can have a layer with a HK of 20 kilovolt at the bottom and 10 kilovolt at the top. So, you see the coercivities HK of the two materials that we use are different, or you can have many layers, or you can have a gradual increase from gradual decrease from 20 kilovolt to 10 kilovolt. So, gradually changing and so on. Okay. So, this kind of material where you have many layers with a different anisotropy field, they will switch independent of each other. Okay. So, it is like a domino falling down. So, let us say we have a set of dominoes like this. So, this video is not working. Okay, let us say we have lot of domino like this. I push this one, what will happen? This layer will fall, this will fall. So, gradually it will cascade to the next layer. So, in a similar sense, when we have layers with various anisotropy, when you apply magnetic field, first this layer will respond, then that will have an impact on the next layer, and that will have an impact on the next layer, and so on. Okay. Okay, so, here if you look at the color code, initially all are red, means magnetization is pointing up. When you apply magnetic field, now you see this layer is pointing at this angle, this is still pointing up. So, you can see gradually the reversal happens. Okay. So, this layer reverses first and so on. So, this kind of reversal mechanism is called incoherent reversal mechanism. So, to achieve that, they have many magnetic layers. So, it is like you can have one magnetic layer here, another one here, another magnetic layer here, and so on, with various values of anisotropy field. Okay, so, that is why there are many layers. Okay, so, that is why I say here there are many layers. So, these layers help to achieve better writing of data. I have some very interesting video to show. Okay, maybe after the break I will show you. Okay. Now we will have a break. See you later.